Let's see how to find the Maclaurin series solution to a differential equation. And this is the second video we're seeing on this topic, and this time we're going to be solving a second-order differential equation. Indeed, we're told find the first 5 terms of the Maclaurin series solution to the second-order differential equation that we see here, with the 2 initial conditions that we see here. Those being that y is equal to 1 when x equals to 0, and that y dash, or the first derivative, is equal to 2 when x equals to 0. Okay, now as I often do, I'll go ahead and write SOL for solution, and now we can get started. In the upper right-hand corner of the screen, you can see that I've written down the first 4 terms for the Maclaurin series of a function f of x. And so the whole idea here is for us to come up with a good approximation to the solution curve y equals to f of x using the first few terms of the Maclaurin series. Consequently, we'll need to find f of 0, f dash of 0, the second derivative evaluated at 0, the third derivative evaluated at 0, and in fact we'll also have to find the fourth derivative evaluated at 0, since we're being asked to find the first 5 terms of the Maclaurin series solution. So let's go ahead. On the far left-hand side here, I'll start with f of 0. Well, f of 0 is given to us in the initial condition we see here. Indeed, we know that y of 0 is equal to 1, which tells us that the solution curve passes through the point with coordinates 0, 1, and of course it tells us that f of 0 is just equal to 1. And I'll quickly underline that. This 1 is the first coefficient taken care of. I carry on and look into the first derivative evaluated at 0. Well, for f dash of 0, we look at the second initial condition we have here, which tells us that y dash of 0 equals to 2, and hopefully it's clear that this is exactly the same thing as stating f dash of 0 equals to 2. And so I can quickly write that as well, f dash of 0 equals to 2. Done. Okay, we now need the value of the second derivative evaluated when x equals to 0. And so for the second derivative, f dash dash of x, we'll need to use the differential equation that's given to us in the question. Indeed, since f dash dash of x is equal to d squared y dx squared, indeed, those are the same thing, hopefully it's clear that by rearranging the differential equation we have here, we can write this second derivative in terms of the first derivative and y. And we can go ahead and state that this is equal to 3 dy dx minus 2y. Okay, now that we have an expression for the second derivative written in terms of dy dx and y, we need to evaluate this second derivative when x equals to 0. But keeping in mind that when x equals to 0, y has to equal to 1, remember that's the initial condition, the second derivative evaluated at 0 will be equal to d squared y dx squared evaluated at the point with coordinates 0, 1. Indeed, since we know that when x equals to 0, y equals to 1, when we speak of the second derivative at x equals to 0, it means the same thing as the second derivative evaluated at the point with coordinates 0, 1. And since we've just seen that the second derivative is equal to 3 dy dx minus 2y, evaluating the second derivative at this point is the same thing as evaluating 3 times dy dx, evaluated at the point 0, 1, minus 2 times y evaluated at 0. And we know the value of dy dx evaluated at the point with coordinates 0, 1. Indeed, that's given to us by the initial condition here. It's equal to 2. And we know the value of y when x equals to 0. Indeed, that's equal to 1. And so this quickly turns into 3 times 2 minus 2 times 1. In other words, carrying on up here, we can quickly state that the second derivative evaluated when x equals to 0 is equal to 3 times 2 minus 2 times 1, which is 4. Done. Okay, we now have f of 0, f dash of 0, and the second derivative evaluated when x equals to 0, and so we carry on and seek to find the third derivative, which I write like this. Now the third derivative can also be written as d cubed y over dx cubed, and to obtain an expression for this derivative, all we have to do is differentiate the expression we had for the second derivative down here. And in fact, maybe I'll box that second derivative. That was the one right here. And I'll box it in green. There we go. And so differentiating the right-hand side here with respect to x, we quickly find that the third derivative is equal to 3 times the second derivative, d squared y over dx squared, minus 2 times the first derivative, dy dx. There we go. That's our expression for the third derivative. Now, to find the third derivative evaluated when x equals to 0, all we have to do is evaluate this expression at the point with coordinates 0, 1. And so let's see, that will be equal to 3 times the second derivative when x equals to 0 and y equals to 1, which is the value we just found. Remember, that was 4. And so I'll quickly write that. That's 3 times 4 minus 2 times the value of the first derivative when x equals to 0, which was given to us in the question. That was 2. So that's 3 times 4 minus 2 times 2, which is 12 minus 4, which of course is equal to 8. Done. We're nearly there. We now need an expression for the fourth derivative, which can also be written as d raised to the power of 4y over dx to the power of 4. And to obtain an expression for this derivative, we differentiate the expression we had for the third derivative up here. So let's go ahead. Differentiating the right-hand side we have here with respect to x, we quickly obtain 3 times the third derivative. There we go, 3 times the third derivative, minus 2 times the derivative of dy dx, which will be 2 times the second derivative. 2 times the second derivative. There we go. That's the expression for the fourth derivative. Now, carrying on up here, we can now evaluate the fourth derivative when x equals to 0, and for that, all we have to do is evaluate each of these two derivatives when x equals to 0 and y equals to 1. And as I'm sure you can see, we've already done that. Indeed, we saw that the third derivative evaluated when x equals to 0 is 8, and we've seen that the second derivative when x equals to 0 is equal to 4. So this becomes 3 times 8 minus 2 times 4, and that's just equal to 3 times 8, which is 24, minus 2 times 4, which is 8, so that's equal to 16. Done. Now, of course, we could carry on forever this way, but since we were only asked for the first 5 terms of the Maclaurin series solution, hopefully it's clear that we can stop there. Indeed, we have 1, 2, 3, 4, 5 of the derivative's values. And so now, for the solution, all we have to do is copy the Maclaurin series we have in the upper right-hand corner, and we could replace the left-hand side by y instead of f of x, and we'll replace the values of f at 0 and its derivatives at 0 by the values we've just found. So let's go ahead. We can go ahead and state that y is equal to f of 0, which is 1, so it's equal to 1, plus f dash of 0 times x, so that turns into 2 times x, so let's quickly write that, plus 2x, plus the second derivative at 0 over factorial 2 times x squared, and I like to write that as 1 over factorial 2 times the value of the second derivative, which was 4, so that's 1 over factorial 2 times 4 times x squared, plus the value of the third derivative at 0, which remember we found here is 8, and that's 8 over factorial 3, and so I'll write that as 1 over factorial 3 times 8 times x cubed, plus the value of the fourth derivative evaluated at 0 over factorial 4 times x to the power of 4. So I'll go ahead and write 1 over factorial 4 times the value of the fourth derivative evaluated at 0, which was 16. So that's 1 over factorial 4 times 16 times x to the power of 4. And again, we could carry on forever that way. And all that's left for us to do now is simplify each of these factors. And so let's see, we have 1 over factorial 2, which is the same thing as 1 over 2. So this is 1 over 2 times 4, which is just 2, so we'll have 2x squared here. And in fact, let me already write that. We'll have y equals to 1 plus 2x plus 2x squared, plus 1 over factorial 3, which is 1 over 6. So that's 1 over 6 times 8, which turns into 8 over 6, which is the same thing as 4 over 3, or 4 thirds, of x cubed plus 1 over factorial 4, and since factorial 4 is 24, that's 1 over 24 times 16, which is the same thing as 2/3 times x to the power of 4, and of course we could carry on forever that way. And as such, we're done. We've now found the Maclaurin series solution to this differential equation.